Welcome, everyone. My name is Kate Rod, and I'm a program specialist at CPAESS. In my role, I have the pleasure of working with our postdoctoral and doctoral fellows. I'm delighted to have you here today at the CPAESS Discovery Seminar Series. CPAESS scientists do everything from exploring the ocean depths to flying into hurricanes. We have heliophysicists modeling the coronal mass ejections, and we have scientists unraveling the mysteries of the Arctic. We really want to share all of this with the public, with the NCAR-UCAR community, and with our many colleagues at agencies and universities across the globe. Just to orient everyone, we're using Slido, so you can pose questions for our speaker at any time during the presentation. They'll be answered after the presentation. To submit your questions, go to the Slido tab. You'll see two tabs in your upper left corner. And there you're able to enter your name and your question, and we'll have Ari answer all of those at the end. It is my most sincere pleasure to introduce you to today's speaker, Dr. Arianna Varuolo-Clarke, who is a NOAA Climate and Global Change postdoctoral fellow researching at the University of Colorado in Boulder. Ari earned her PhD at the Lamont Doherty Earth Observatory at Columbia University in 2023. Her dissertation sought to understand what has driven the mass precipitation increase observed over southeastern South America and why most climate models systematically underestimate this precipitation trend. In summer of 2025, this August, Arianna will be joining the Department of Geography at Dartmouth College as an assistant professor. Today, Dr. Varuolo-Clarke will be speaking on disentangling warming and circulation influences on precipitation under global warming. Ari, the floor is yours.
Thank you so much, Kate. Hi, everyone. It's a great pleasure to be here. I'm really grateful for the opportunity, and thank you for tuning in to listen. So as Kate said, I'll be talking about my work on disentangling warming and circulation influences on precipitation under global warming. This work has been done at CU Boulder and at NSF NCAR with input and help from many of my collaborators listed here, including my mentors, Jen Kay and Brian Medeiros. And so I want to start off by orienting us with why study precipitation. And I'm going to take some time to motivate the work that I'm currently doing as a postdoc with the work that I did during my PhD and try and tie that thread and help you understand kind of what motivates me to study precipitation, generally speaking. Okay, so starting off, why study precipitation? Why should we care about this? Well, first and foremost, it goes without saying that water is essential to life on Earth, and precipitation helps to distribute and recycle and drives the distribution and recycling of water on the planet. And precipitation variability impacts water management resources, food security, and ecological management. And it's one of the most, because of this, it's one of the most important aspects of climate change to predict, but is also one of the most challenging. And as we know, too little rainfall can lead us into drought conditions, leading to devastating wildfires, but too much precipitation can lead to devastating floods and landslides, making it just underscoring why it's so important to predict and understand how precipitation has changed in the past so that we can better understand how it might change in the future. Specifically, I've thought a lot about long-term precipitation changes, and so why do we want to study those? This is a really nice quote from the Intergovernmental Panel on Climate Change, 6th Assessment Report, or AR6. It says, "It is unequivocal that human influence has warmed the atmosphere, ocean, and land. Widespread and rapid changes in the atmosphere, ocean, cryosphere, and biosphere have occurred." And these are just some cool figures showing 1901 to 1984 precipitation trends in the annual mean versus 1985 to 2014, again in the annual mean. The top row are just two different sets of observational data sets. This GPC product doesn't cover any land, but our newer products do include, or doesn't cover the ocean, but our newer products do include data over the ocean. And then the bottom row is just showing all forcings from several climate model simulations included in the IPCC report. We can see, so over South America, where my PhD research focused, we get some of the wetting trends and drying trends that we in the models that we see in observations, but they're much weaker in magnitude, especially over this longer time period. And then when we look at the shorter time period, we see that the models are still capturing some of the features, but over southeastern South America, for instance, over the shorter period, the models are missing some of the trends that we're seeing in the real world. And then adding to this, in this figure, we can also then look at the changes in the greenhouse gas forcing and that's impact on rainfall versus just the aerosol forcing. And again, these are just showing the two different time periods, and you can see that there's competing impacts under whether or not we'll see a wetting in regions like southeastern South America, which we would expect under greenhouse gas forcing, but we might see some drying as a result of aerosol forcing, and the time periods of these forcings and these trends are also really important to consider. So this is just to make the point that at regional scales, precipitation trends are dominated by internal variability, or kind of the chaotic nature of the atmosphere, and that they can be obscured by these contrasting responses to greenhouse gases compared to aerosol forcing. And so to get into that a little bit more, I want to highlight these challenges of quantifying drivers of precipitation change. So while there is high confidence that anthropogenic forcing has contributed to mean multi-decadal precipitation changes across several regions, including Western Africa and Southeastern South America, CISA, as I'll call it, it's really challenging to robustly assess the magnitude of the relative contributions of greenhouse gas forcing, which includes stratospheric ozone depletion as a result of the ozone hole, and these different species of aerosols, because of, like I've already said, this large role of internal variability in the climate system, observational uncertainty. Our observations are not perfect. There's lots of different sensitivities to them if we've changed the way that we've taken the observations, and different parts of the world have a higher amount of observational records than other parts of the world. Modeling uncertainty. So this is talking about our climate models that we use to look at precipitation, and we make lots of decisions that go into these models, and different modeling centers make different decisions. So there's lots of uncertainty across the models. And then finally, forcing uncertainty is talking about the fact that we don't fully understand how our the social aspect of how climate change will evolve, given how much emissions we continue to emit, and how we then represent these in the model, and then how the model responds to them, all falls under this forcing uncertainty piece. So these are just a way to highlight the challenges of quantifying drivers of precipitation change. Now I want to show our kind of roadmap for today and my motivation for studying and disentangling different drivers of precipitation change. So I want to talk about this precipitation increase over southeastern South America, or CISA, and this is some of my PhD work that, like I said, I'll use to motivate the current work I've been doing, which has focused on this disentangling kind of thermodynamic and dynamic drivers of future precipitation. And I've really ended up focusing on these possible futures of California rainfall, and I'll introduce why specifically California, and I'll show all of those results. And then lastly, I'll introduce this second project that I'm working on, which uses idealized simulations of climate models to ask what California's rainfall would look like in a warmer world, where the same atmospheric circulation occurred, but we just had a warmer atmosphere due to a warmer ocean. So starting with southeastern South America. Here I'm just showing global precipitation trends from 1950 to 2020. I have a box over the region of southeastern South America, which encompasses southern Brazil, Paraguay, Uruguay, and northeastern Argentina. I'm starting with this global map so that we can really orient and see that this region stands out as one of the regions to experience the largest wetting increases over this time period across the globe. We see a similar increase in rainfall over the Southeast US, but then on the west coast of both of the Americas, we see some drying trends. And I just want to point out that I'm really interested in also thinking about the hemispheric symmetry between these wetting trends in the southeast of South America and North America, and the drying trends on the west coast of North America and South America. And then also thinking about what is driving this wetting trend here in southeastern South America could be linked to what's driving this drying in and along central Chile. But for now, focusing on southeastern South America, so this region has experienced a massive increase in precipitation. This is just showing from 1902 to 2020. So on the x-axis, we have time. On the y-axis, we're showing the precipitation totals for, this is December through February, so the austral summer. So the total accumulated precipitation over those 3-month periods for each years in 2 different precipitation data sets from CRU and GPCC. And at first, so we see that there is an increase, this linear trend that is occurring, but there's also a lot of year-to-year variability that sits on top of this precipitation trend. And that's something that adds to this challenge of quantifying precipitation. It's because of this year-to-year variability and the internal variability of precipitation that leads to that. But so over this time period from the early 1900s to around present day, there's been around a 20% increase in summertime rainfall, which might not sound like a lot, but it really is. And why do we focus on the austral summer period, December through February? Here is a time series just showing the annual or the climatological amount of rainfall that occurs during each month. So the x-axis is showing September through August, and we have precipitation again on our y-axis, and we can see a peak in rainfall in this December through February period, which is when the region experiences around 30% of its annual rainfall. And now I'm just showing the seasonal trends. So annual on the top, this is again now from 1901 to 2020, and then showing December through February, March, April, May. This should be June, July through August, and then September through November. So we see that in austral summer, DJF, that's when the largest rainfall increase is occurring. The shoulder seasons of this fall and spring are also experiencing rainfall increases, but we're seeing little to no increases during the winter season, which makes sense because that's their dry season, and December, January, February is really their wet season. And so this precipitation increase is also evident in stream flow records. Here I'm showing records from the Laguna Mar Chiquita sediment record that have showed that the period from 1975 to 2000 was wetter than any period in the last 200 years. Now this is showing the Rio Bermejo tree ring stream flow reconstructions that show an increase in extreme stream flows. Events since 1960 compared to the 1680 to 2001 period. And so this precipitation increases also kind of co-occurred with an expansion in agriculture. So the La Pampas region of Argentina has gone from this kind of native grasslands region that was really used for grazing. And with this increase in demand and increase in precipitation, it's kind of switched over to being a source of agriculture. So there's a lot of soybean production and maize production that comes out of this region now. And there's been these recent extremes in precipitation in the region. So about 3 years ago now in Petrópolis, Brazil, there was a 3-hour period where 260 millimeters of rain fell, causing destructive flooding. And then just 5 days later, another 415 millimeters of rain fell over a 10-hour period in the surrounding mountainous region, where there was terribly destructive flooding and loss of lives. And so we really don't know what's driven this trend. And depending on what model you're using, the time periods you're looking at, and kind of what question you're asking, you might get completely different answers. So back in 2010, Seeger and others said that the wetting trend was driven by natural atmosphere-ocean variability, that there was no evidence of greenhouse gas forcing contributing to this trend. So it was just coming from the natural variability within the climate system. In 2014, Gonzalez and others said that post-1960, the trend could largely be explained by stratospheric ozone depletion. And then in 2016, Zhang and others at GFDL used the GFDL models and said that they can simulate the precipitation trend in response to greenhouse gas forcing and not to aerosols or stratospheric ozone depletion or from natural variability alone. I have an asterisk next to each of these kind of keystone or touchstone papers for me, and that's because each of these papers note that climate models kind of systematically underestimate the precipitation trend. So while climate models are a really amazing tool for understanding past changes and projecting future changes, there appears to be this systematic bias in simulating these decadal scale or multi-decadal scale precipitation trends. So that became the focus of my PhD, was to try and reconcile the previous literature and this assessment of the weak and provide this assessment of the weak trend within the models. So what is the future of CETA hydroclimate? Here is, again, just a time series of this, just to illustrate that we really don't know what the future is, right? It could continue on this upward trend, or we might see a decline and where we have a reversion towards drier conditions again. So to dive into some of the results from my PhD, just as a way, again, this kind of long motivation to get into my current work, the data products that I use for this project were the Climatic Research Unit product and the Global Precipitation Climatology Center product. And then I want to introduce the models because these are the real star of the show. I used CMIP5 and CMIP6, so the coupled model intercomparison project phase 5 and phase 6. These are fully coupled models which allow us to understand the role of greenhouse gas forcing, aerosols, or land use change. And these were run from or examined from 1901 to 2005 or 1901 to 2014. And we looked at over 600 runs. Then we looked at these future projections, the shared socioeconomic pathways. These different values represent the different amounts of radiative forcing that would occur at the radiative imbalance at the top of the atmosphere at the end of the century under these different greenhouse gas forcing pathways. So we're looking at the effect of increased greenhouse gas forcing from 2015 to 2100, and we looked at nearly 700 simulations. Then we looked at some SST forced runs. So we prescribed the model with the historical sea surface temperatures, and then we have the greenhouse gas forcing evolving in the atmosphere so that we can quantify the role of sea surface temperatures and anthropogenic forcing. These simulations were from 1901 to 2012, and we looked at 32 ensemble members, 16 from each of these versions. And then lastly, we look at pre-industrial control runs as a way to look at just the natural atmosphere ocean variability without any greenhouse gas forcing or aerosol forcing. And these simulations range from 100 years to 1200 years. Now I'm going to present a series of results as box plots. And so before I get into that, I want to orient you all with what that looks like. So on the x-axis will be the different data sets. The observations, CRU or GPCC will always be on the leftmost hand, and then we'll have the different modeling outputs. And then the precipitation trend is on the y-axis, so positive is wetting and negative is drying. Here now for the observations, I'm calculating these 85-year sliding window trends over the periods 1902 to 2019 or 1902 to 2016. And so these are calculated at 1-year increments where I will take, you can imagine taking the time series that I looked at and calculating the trend from 1902 to 1987, and then calculating it from 1903 to 1988 to get those 85-year window trends. And then for the models, I'm just calculating that from the 185-year period for each of the ensemble members. And then by looking at the sliding window trends for the observation, it gives us this range of uncertainty for the observations, which is really useful since we have a kind of single realization in the real world that we want to compare to many realizations of possible climates from the climate models. So the first question is, what is the precipitation response in the CMIP6 historical simulation? So here we have our box plot filled in. We have CRU and GPCC all the way on the left. We have the ensemble mean results. So considering all of the members, then the low top versus high top models, which is just getting into the details of the kind of modeling schemes. And then I have the individual model runs organized by models that have the lowest number of ensemble members versus the most number of ensemble members. So CAN ESM5 has 65 ensemble members. The takeaway is that we have this increase in the real world that's around 2% per decade, and nearly none of the models are able to simulate precipitation increases as large as that. So we get about 6 simulations from 5 models that do fall within this observational range of uncertainty, but largely the models are simulating a muted precipitation increase in response to the anthropogenic radiative forcing. Next, what is the precipitation response in the CMIP6 projections? So here we have the observations again. Now in this historical space, we have the CMIP5 and CMIP6 results. So these are just the, we take the mean results from each model. And so we just have the one dot representing each of the models considered by taking the mean of each of the ensembles of the models. And then we also look at the projections for the future in CMIP6. And you can see that, again, when we compare it to this observational range of uncertainty, it's not until even under the highest emission scenario that we're really getting precipitation trends of the same magnitude of observed, which speaks to this possibility of the models kind of not responding to the forcing or having a muted response to the forcing over the historical period, and leads to these questions of, if the models are missing some kind of forcing over the historical period, what could the future really look like? So models simulate increased precipitation in CISA in response to increased radiative forcing, but only overlap with currently observed trends at the highest emissions scenario. Next, we ask, what is the precipitation response to SST forcing? And so we introduced this one as my example box plot earlier, and we can see that with the SST forcing alone, the models are still unable to fall within this observational range of uncertainty, suggesting that while SST forcing contributes to some of the trend when we look at the kind of ensemble mean, it's contributing to some of the positive trend, but not enough to get us. The atmospheric variability that sits on top of that forcing is not large enough to bring us into this observational range of uncertainty. So SST forcing, as represented in these two ensembles of the same NCAR climate model, or different versions of the NCAR climate model, they can simulate a fraction of the trend, but we're still missing something. Next, what do precipitation trends look like without any forcing? So this is looking at our pre-industrial control runs. And again, we have the observations here. Now we've calculated similarly the sliding window trends across the pre-industrial control runs. And we can see that even when we look at all of these ensemble members, or all of these calculations of the trends across all of these 65 runs, it's only the very tail end, or the kind of outliers of the trends, that are able to fall within this observational range of uncertainty. So internal variability is playing a role and can give us this trend sometimes, but it's not that likely, and it's still not quite as large as observed. So some of the pre-industrial control runs can simulate trends that fall within the observational range, but many do not. So what we're seeing here is that models systematically underestimate the CISA precipitation trend. And like I said in the slide with the kind of timeline of research in this field, this is consistent with previous research that models tend to really systematically underestimate this precipitation trend. And so some of the possible conclusions that we've come up with are that the observed trend might be strongly driven by anthropogenic forcing, but the models may be underrepresenting the forced precipitation response, specifically in southeastern South America. And then internal variability may have also dominated the observed trends, like we saw in that last box plot. And so potentially the models are systematically underestimating internal atmospheric variability. And so likely the answer is some combination of both of these things. It's both the forcing and the internal variability has driven to these trends, and we need to better understand where the potential bias within the models is. And models kind of systematically underestimate century scale precipitation precipitation trends more broadly, zooming out. So this is a feature that has persisted for a while, where models tend to have this low bias in these century scale precipitation changes. And Knudsen and Zhang in this 2018 paper noted that if these low biases were to persist into our projections, we run into the risk of underestimating flood risk and then overestimating drought risk. And one potential idea of why these low biases exist may be a result of models underestimating internal variability on multi-decadal timescales. And I've included this figure from a paper I really like, Guo et al. 2019, where they use this technique called dynamical adjustment, which I don't have time to get into the details of, but what they're showing here is the total precipitation change for the extended winter season, November through March, from 1921 to 2015, in the precipitation trend and the sea level pressure trends. Then they tease apart what the dynamic component of that, and you can see that there's a trend or some trend in the dynamics, in the circulation and the sea level pressure, and also some trend in the precipitation in this dynamic component. And then the leftover component they call the residual, which we could think of as the thermodynamic component. And they note that the models, so this is all in the real world or observations, that in the models in the ensemble mean are able to capture the residual or thermodynamic term quite well in terms of the magnitude and the spatial features of the changes. And so they suggest then that what we're missing in being able to get these trends is a result of the dynamics or of this internal variability. And so that's kind of the focus that I want to move to in this next section, where we're going to think about the possible futures of California rainfall given the role of internal variability. And this is a bit of a pivot, but it all ties into this big picture question I'm really interested in, is understanding precipitation changes over the past so that we can better understand the future. And so this is kind of taking a leap forward to thinking about the future changes, but I think that there's some really valuable work in space here in this kind of framework that I'm developing that we can use to also think about past changes. Okay, so coming back to the Northern Hemisphere, we're going to focus on a region with a large amount of internal variability, which is the west coast of the US. So this is a map just showing the total precipitation change for December through February. So we're still thinking about DJF, but now it's boreal winter instead of austral summer. So this is just the standard deviation of that total precipitation change across the CESM2 large ensemble, which I'll introduce more thoroughly in a moment. And so these high values of around 0.7 are some of the highest values that we see for this season across the Northern Hemisphere, speaking to the large amounts of variability in this, in terms of what the future precipitation in this region might look like. So what I want to ask are, what are the possible patterns of precipitation change across the North American West Coast when we consider the role of internal variability and go beyond thinking about just the ensemble mean? And so to do that, we extract the internal variability by decomposing precipitation change into its thermodynamic and dynamic components. So what are those? So these are just two first order mechanisms that we think of as contributing to precipitation change under global warming. So we have thermodynamic versus dynamic. This is a really fun figure from Climate Central, just showing or kind of a schematic of the fact that a warmer atmosphere, warmer air can hold more moisture. And so these changes just simply follow the theory of Clausius-Clapeyron, which suggests that a warmer atmosphere can hold more water vapor. So if there's a warmer atmosphere, we might expect more rain or heavier rain because of that. Dynamic changes, on the other hand, are shifts in the atmospheric circulation that will affect the horizontal and vertical transports of water vapor. So modeling studies suggest that these are things like a poleward expansion of the Hadley cell, which will then lead to a poleward shift of the storm tracks in both hemispheres. And I left out the reference for this. This is a figure from the IPCC. Okay, so in order to quantify dynamics versus thermodynamic contributions to precipitation change, we're doing this analysis fully in a modeling space. So we're using the CESM2 large ensemble, which is a fully coupled Earth system model that comes out of NSF NCAR. It's one of the leading models kind of in the modeling space. We're looking specifically at 50 members from the large ensemble, which follow the CMIP6 forcing protocols. And for the future period, so post or 2015 and onwards, we're following, or this ensemble follows the shared socioeconomic pathway of 3-70, which means there's a 7 watt per meter squared radiative imbalance at the top of the atmosphere by the end of the 21st century. To do these calculations, we're using daily data, so daily 500 hectopascal vertical velocity, which is a measure of the upward and downward motions at that level, so whether or not we have ascent in the atmosphere or descent. We're then looking at daily precipitation, and we're considering the mid-latitudes broadly, so in both hemispheres from 20 to 70, and today I'll just focus on the northern hemisphere. And we're comparing two periods. Our historical period is 1981 to 2000, and our future period is 2081 to 2100. And this is just a really nice schematic that I like showing kind of what our climate models look like, right? So we break the globe up into these different grid spacings. So we have our horizontal grid spacing of the latitudes and longitudes, and then several layers of the atmospheric layer, and then also into the ocean and the land. And then we solve these equations at each grid space that represent the physical processes of the atmosphere or the ocean. And I'm focusing on boreal winter, December through February. Okay, so the steps to make these calculations are we first obtain a probability distribution function, or PDF, of vertical velocity for a historical and future period. This is just an example for the Northern Hemisphere mid-latitude. So we have the x-axis is the daily vertical velocity in hectopascals per day, and then the y-axis just shows that relative frequency. Positive values, we've oriented them such that positive means ascent, and then negative values would mean descent. And we can see that most of our values are falling around 0, but we have these tails of very high versus very low values. The black line is the historical period, and the gray dashed line is the future period. Once we have this PDF, we next composite the daily precipitation for each omega bin for both periods, and that will look something like this. Where now the vertical or the x-axis is still that for daily vertical velocity, and now the y-axis is showing the daily precipitation in millimeters per day. And we can see that where we have ascent, that's where most of our rainfall is occurring, and where we have descent, we have little to no rainfall occurring. So this kind of breakdown makes sense and works, especially on this daily time step. And so you can see black again is the historical, and then gray is the future. So for the same amount of vertical velocity, or the same amount of ascent in the future, we're getting more rainfall, and that ties into that part of that idea of the thermodynamics, right? A warmer atmosphere given the same amount of ascent could lead to an increase in rainfall occurring. Once we have these 4 distributions or histograms, we get these at each grid space. Then we can calculate the dynamic change as the change in the mean precipitation due to the change in the PDF. So that will look something like this. So you're just taking the difference in those PDFs, so that left-hand distribution or histogram, and considering that historical binning of precipitation. The thermodynamic change is simply the opposite. It's the change in the expected precipitation for a given omega. So now we're considering the difference in that right-hand histogram. And then considering the historical kind of circulation features. We do that at every grid cell in our region of study across each ensemble member. So first I'll walk through some of these results in the mean space, and then we'll dive into what the different patterns look like. So we just starting with looking at the total change in precipitation. So again, this future period versus the historical period. we see some key changes. There's largely an increase in rainfall over land. There's a decrease in rainfall over the Mediterranean regions, so specifically over the Mediterranean and then a bit through kind of northwest Mexico and Baja California region. We see a decrease in rainfall kind of equatorward of the storm tracks and an increased poleward of the storm tracks, suggesting that poleward shift in the storm tracks that we expect, but we can't quite say that here because we're not looking at the circulation metrics. Now we can look at the thermodynamic contribution. Again, this is the mean result across the 50 ensemble members, and we can see that the mean thermodynamic contribution is largely capturing much of the total precipitation change that we're seeing, especially over land and over the Atlantic. I don't quite know what's going on and why there's such an increase over the North Pacific as a function of thermodynamics, and that's something that I'd like to look into in the future. And then in the dynamic contribution, we're seeing little to no contribution, especially over land, but largely over most of the hemisphere here. So there's little to no contribution from dynamics in the mean space. There's this negative contribution in the North Pacific, again, likely related to the shifts in the storm track that we're seeing. But overall, in this mean space, we see little to no contribution from dynamics, large contribution from thermodynamics. Now I'm just zooming in to the west coast of North America, as this is where I'll focus for the rest of the talk. And you can see even more clearly that the thermodynamic contribution is really capturing that total change, and the dynamic contribution is really minimal, especially over the US. We're getting some contribution over Northwest Mexico, though. And then lastly, you might remember this figure from the beginning of this section, where I'm just showing the standard deviation in the total precipitation change for across the 50 ensemble members. And we can see that there's a large amount of variability that's occurring along the West Coast, and it's largely coming from the dynamic term, not the thermodynamic term, which leads in and feeds into this idea that the thermodynamic or the thermodynamic contribution, as we've calculated it, really captures that forced response. And there's a lot of important information that sits in the dynamic contributions and that variability that gets washed away when we're looking at the mean space based on the fact that we get such drastic changes possible here, and it's largely from the dynamic contribution. So the next question is, what spatial patterns are leading to the variability in the projected precipitation change? So to look at that, we are using a machine learning algorithm called self-organizing maps. We feed this algorithm all 50 maps of the precipitation change across the large ensemble, and then we tell it, I want 6 maps back, so pick out basically the 6 persistent patterns. I've done this analysis with 9 maps as well and get quite similar results. And I don't have too much time to go into the specifics of the machine learning algorithm, but it is a really cool way to pick out these patterns, and it's very similar to an EOF or PCA analysis. So in our top, these are organized as SOM 1, 2, 3, 4, 5, 6. The percent values are telling us the frequency of occurrence of these different maps. And the top row, you can see there's precipitation increases kind of centered on Northern California. In SOM 2, those also extend through the Pacific Northwest. These patterns are pretty persistent. In the middle row, more modest than what we see in the top row, but still kind of those overall precipitation increases that we expect based on what we saw in the forced response. And then lastly, in the bottom row, we see these driest Californias in the future. And so these are occurring about 28% of the time combined between SOM 5 and 6, and then SOM 1 and 2 are occurring about 34% of the time. So these are the least likely to occur, but we can't necessarily discount them as not being possible. So the next part of this is now I just want to focus on this top row and bottom row and think about what are the thermodynamic and dynamic contributions across these. So to do that, now I just have the top and bottom row again for the total precipitation change. Now this is the thermodynamic component. So we cluster over the ensemble members identified by the SOM algorithm. And so now we're just showing what the thermodynamic contributions look like across these. They look pretty consistent. The largest difference is kind of at what latitude that kind of drying to wetting occurs from the subtropics to the mid-latitudes, but overall there's a lot of consistency. This is in contrast to the dynamic component, where we see much more variability across these patterns, right? Where the top members, the wettest members, there's some dynamics that are contributing to this wetting versus the driest members, the dynamics are contributing to the drying that we see across all of Northern California. And despite the fact that the thermodynamic contributes to some drying throughout California, it's not explaining all of the drying that we see in the total precipitation maps. And that difference is coming from the dynamic component. And then now we're showing the relative precipitation change. So what I've done here is remove the ensemble mean from the total precipitation change. So the ensemble mean of the precipitation change is removed from each of the individual maps of change, and it shows you, so this relative precipitation change, or the variability of the precipitation change, is about the mean. And what's really cool is that you can see that the dynamic component results are largely capturing this internal variability within the climate model. And we next want to ask, what are the large-scale atmospheric circulation changes across these SOMs? And so now we're looking at all 6 members again, or 6 SOM patterns again, the total precipitation change. And now this is just the change in the 500 millibar geopotential height metric to show. So these negative values are indicating a deepening, or this negative trend is leading to anomalous kind of anticyclonic circulation, or excuse me, anomalous cyclonic circulation, leading to a kind of eastward extension and strengthening of the subtropical jet here. And we can see these features kind of exist throughout each of the kind of patterns of change, but they're strongest in these most wet cases. And yeah, so in SOM 1 and 2, we're getting a strong negative trend that allows for the subtropical jet to extend eastward and strengthen. And then this is now just showing the relative change. So similar to what we did with precipitation, we just removed the ensemble mean change so that you can see that we get these really negative values in this top rows compared to these positive anomalies in the bottom row, just speaking to the differences of circulation changes that we can get across one ensemble. And then we do the same for the 500 millibar zonal wind change. So this is just showing the change in the wind in just the zonal winds. So where we have these positive values, we have represents the kind of westerly flow of the jet, which is, and in the future, in these wettest ensemble members, that's kind of strongest, more northerly here, and there's a real shift of that in these driest members, which would contribute to that decrease in precipitation that we occur. And you can see that again a little more clearly when we look at the relative change. So we have these more positive values throughout the jet region in both the top members, and then more negative values, so a decrease in that kind of flow in those drier members. So the wettest futures are associated with a strengthening and eastward extension of the subtropical jet, and the driest members don't see as strong of a circulation change. And so with that information, I'm interested, one thing that came up was being interested in thinking about what California rainfall would look like in a warmer world, where we have the same kind of atmospheric circulation, but we feed the model warmer sea surface temperatures. So the driving question here is, using these idealized experiments, what is the influence of warming alone on precipitation change across the North American West Coast? And so again, what would precipitation look like in a warmer world, but with the same circulation? So the experimental design that we're following, we're using the CESM2 Community Atmosphere Model version 6. So this is just the atmospheric model. And so we have this AMIP nudged HIST run versus this AMIP nudged future run. And so in both of them, the winds at every level from 850 hectopascals to the top of the atmosphere are nudged to reanalysis from every error 5 every 6 hours. And then the AMIP nudged HIST run is run from 1979 to 2014. Whereas this AMIP nudged future run is run, the winds are from 1979 to 1998. In the historical run, we're looking at prescribed historically observed sea surface temperatures and sea ice extent over this period. But in this future run, we're looking at prescribed sea surface temperatures and sea ice extent. We're using the prescribed SSTs and sea ice extent that are taken from the ensemble mean of the CESM2 large ensemble from 2081 to 2100. So we have this 20-year period of the projected mean SSTs and sea ice extent. And so I'll just quickly share some of these kind of preliminary results. So this is the DJF, so boreal winter precipitation climatology from the historical run versus the future run. And then this is just showing the difference. And it's really interesting to see this kind of drying throughout the storm track region, despite the fact that we've given the model the same circulation. And one of my colleagues has suggested that this is a fact of, even though the circulation is the same, we're going to have a much warmer, there's a greater temperature gradient here because the poles warm so much faster than the tropics, so that you get this strong gradient here. And so you get more of a poleward direction of the moisture, even though the jet is consistent. And when we zoom in to look at the West Coast, we see a similar, we see that transfers really clearly here, where we're seeing drying over the North American Southwest. So again, this is under the historical, the same historical large-scale circulation patterns, but a warmer ocean. And the hypothesis going into it was that precipitation would have increased here, because if you had the same jet, all else being equal, you have the same jet but a warmer ocean that it's going over, I would have expected an increase in rainfall. But that's not quite what we see. And these runs are still relatively new. I just ran the second one in January, so we're still kind of thinking about and interpreting what the story is behind this, but I just wanted to introduce that. And so kind of the next steps with these results are: what are the precipitation trends in each nudged run? What does the tropical Pacific look like for each nudged run? And can we use idealized simulations where we nudge horizontal winds to better understand hydroclimate trends, which kind of goes back to some of the earlier work I've done thinking about trends. And so with that, I will thank you so much for your attention, and let me know if you have any questions.
Thank you so much, Ari. That was so interesting and such important work. We really appreciate you sharing that. Now for our question and answer portion of today's seminar, you can either go to that Slido tab, or else we have a QR code that you can scan and add additional questions. I'd also like to ask everyone attending to check out our webpage found at cpaess.ucar.edu for our upcoming seminars. We have more great speakers coming up, but right now I wanted Ari for you to address the questions we have at hand.
It looks like we have one question. What are the most important changes you would like to make in models to increase their accuracy for precipitation changes?
That's a great question. Thank you. I've looked a bit at the role of horizontal resolution. So if we increase the resolution, does that improve trends for Southeastern South America? That wasn't necessarily the case. I think there's a lot of great work to do in that space, thinking about the Southwest US and the West Coast of the US, just with the effect of the mountains and topography. So actually in both both of the Americas, that's really important. So that's one thing that I'd like to explore more. And then the other piece is thinking about the way that precipitation is parameterized in these models. And there's lots of different kind of schemes that exist. And so doing a deep dive into what are the potential roles of those for simulating precipitation trends, I think is really interesting.
And it looks like we have another question here from Lily Hahn. Great talk. Thank you. Have you also looked at ocean circulation anomalies associated with the different SOMs?
No, it was actually a little bit, and the results that we saw suggested, well, thinking about the North Pacific, it looked kind of like we were seeing ENSO pattern versus or excuse me, an El Nino pattern versus a La Nina pattern. But in talking a bit about that with Clara Desser, she suggested that what we were just seeing is actually the atmospheric circulation. Feeding on or impacting the sea surface temperature circulation, or what we were seeing in the sea surface temperatures. So I think there's more work to be done there, and I've tried to look a little bit at the across the SOMs at how different the kind of SST gradients are in the tropical Pacific, and again didn't come up with any clear distinction of those differences across those SOMs, but I still have a lot of questions around the SOMs, so that's a good reminder of that question. Thanks, Lily.
Please ask questions if anybody has any. Oh, here we go. Similarly, have you considered the role of SSTs and/or marine heat waves on a finer temporal scale in influencing changes in future precipitation?
I haven't, but that recently came up in a conversation with someone this week about over specifically for the Southern Hemisphere and South American climate, and thinking about the changes in SST patterns we've seen in the South Pacific. So that would definitely be something to dive into deeper. And I haven't, and a lot of this has been, more on multi-decadal scales. So it would be fun to dive in and look at those finer temporal scales. Thank you.
Excellent. Folks, please do ask more questions if you have them. In the meantime, I will just give you guys a heads up about our next scheduled seminar, which will be on Wednesday, March 19th at 11 a.m. Mountain Time with Dr. Holly Olivares, who is also a NOAA Climate and Global Change postdoc. And they will be speaking on solar radiation modification and ocean biogeochemistry. And I also want to let you guys know that this talk and all of the other CPAESS seminar talks, you can find them on our webpage and on our YouTube channel. So I know sometimes this is in the middle of somebody's workday, so just know that you can check them out later.
Thank you, Dawn.
Yeah.
So that's the end of the questions, it looks like. So I wanted to say our sincere thanks for you sharing your important research with us. And also thanks to Fletcher Ryan of UCAR's Multimedia Services for his invaluable assistance and making this seminar happen and recording it and providing it to everyone. And I hope we all get to see you in the future. As Dawn mentioned, coming up in March, we have Dr. Holly Olivares. So stay tuned for some more great science. Thanks so much.
Thank you.